Thank you all for joining today. This is the third open house of the Genomic Knowledge Standards work stream, which I have the honor of co-leading along with Alex Wagner. And and so are you seeing my slides before I go on? Good,
Yes.
good, thank you. So so the goal of these open houses is to provide a high level overview of what we're doing for, well, especially targeted to people who maybe know the first thing about the GKS work stream and are curious to learn the second thing. And and all of these open houses will be, well, are recorded and shared on our YouTube channel. So they're accessible after the meeting. And so today, after I do a quick overview of the work stream, Daniel will talk about Cat-VRS, which is one of our new products. Then we'll hand it over to our colleagues at Epic to describe how they're using the GKS products in their work. And one of our goals in the GKS work stream is to always end our meetings at the 50-minute mark to give people a chance to catch their breath before their next meeting. So that is our aim here also. And and so who we are. So the goal of the GKS work stream is to, define, you know, language and standards for sharing knowledge relating to genetic variants and and really to describe what we do. We have this beautiful video just produced by the GA4GH communication team.
Elise is a clinical laboratory director testing a patient for a genetic disease. She finds a change in the patient's DNA and wants to understand how this variant might cause the patient's symptoms. However, Elise struggles to find knowledge about the variant because other healthcare institutions describe genomic variants and related evidence differently. Standards from the Global Alliance for Genomics and Health, or GA4GH, help by defining a common language to describe variants and their relevance to clinical care. By tapping into a network of institutions that use these standards, Elise quickly discovers and brings together knowledge about the variant. She shares her findings with the patient's doctor, who makes a diagnosis and personalized treatment plan for the patient's care.
Great. So, um, so with that introduction, why is sharing genomic knowledge challenging? That first off, variant evidence comes in many different formats relating to many different reference sequences and distributed around many locations. So any solution to this challenge must operate across those data structures and must incorporate that reference sequence context and and be globally consistent, across all of these different locations. So that's the current challenge, and it's going to continue to grow with new new standards, with new knowledge, such as what's coming out of the Human Pangenome Project. And and so how we're addressing that in GKS, we have three areas of genomic knowledge standards: variant representation and annotation and sequence annotation. So so here are our current products and study groups. Yeah, the variant representation specification verse, you know, gener generates um, um, unique identifiers for finding genetic variants in remote databases. Version 2.0 was released in March and extends the functionality to structural variants as well as simple alleles and small indels. Cat-VRS, categorical variant representation, you'll be hearing more about shortly, and the variant annotation specification provides a structured modeling framework for conveying knowledge on variant annotations with their underlying evidence and provenance. And and our study group, a sequence annotation, is is evaluating the limitations of interoperability for describing genomic knowledge, genomic features, and their white paper is currently under PRC review, which in GA4GH product development means that we're we're working on getting the encapsulated statement of the problem down before any next steps. So something that I want to stress, it's very uh, a core emphasis in our work stream and our roadmap is that everything we do is rooted in community needs. So, for example, here is some in for developing verse 2.0, we we surveyed the implementers, which is um, actually means you, people or organizations who will be using the standards and and assessed what is the functionality they find most valuable, and that is what drove our product development milestones. We developed this work in a very collaborative and community-driven mode that incorporates our monthly virtual work stream meetings, hackathons held in conjunction with Connect and other meetings, and monthly GKS think tanks, which are essentially short monthly virtual hackathons, and a great way to get get started if you're if you want a little support getting rolling with GKS work. And and here are a number of our current um, implementers. So with that, any any questions or comments before we move along? All right. And so with that, I'll stop my share and pass the pass the floor over to Daniel.
Just trying to find my folder, or not my folder, my window here that I'll be able to see. Come on, let me share this. Oop. There we go. All right. Everyone can see that? Very good. All right, cool. So, good morning, everybody. Oh, well, good morning, good evening, wherever you may be, people. My name is Dana Puthwala, and I'm one of the co-leads for the Cat-VRS product development group. And I'm going to spend the next 15 to 20 minutes, hopefully more on the 15-minute side, giving you an overview of what Cat-VRS is about, what it does, how it can help you, and answer any general questions you may have about it. So first, we'll talk about what categorical variants are and why they're a problem that we had to solve here in GKS. We'll talk about how the Cat-VRS works and how it solves that, and what Cat-VRS can do for you. So first, our problems. So in genomic medicine, the question we're often trying to answer is, We look at some patient, we find some variant, and we want to know, is this a variant we've seen before? Because if it's a variant we've seen before, we usually have genomic knowledge about that variant, phenotypes it might be linked to, therapeutics we might be able to use for it. And so what we need to know is whether we've seen this before or not. And this is complicated because oftentimes the variants are slightly different. So we really want to know if it's the same type of variant as something we've seen before. And when we refer to an entire group of variants at once, this is what is a categorical variant. So a categorical variant is just a group of underlying genomic variants that are similar in some clinically interesting way. So examples of some common and less common categorical variants include BRAF V600E, EGFR gain of function, TP53 loss, or MET delta X14, and more about that in a minute. Now, the reason why Cat-VRs are important, Cat-VRs categorical variants, why these are important is because they're core to variant interpretation. When someone publishes a paper and they say, MET amplification is associated with this bad thing happening, they're using a group label of variants to associate that with genomic knowledge. And this extends to the way that genomic knowledge is organized in a lot of our knowledge bases. So really figuring out a way to represent categorical variants efficiently is an important part of genomic knowledge organization. So categorical variants link to our knowledge to phenotypes, therapeutic indicators, annotations, evidence items, and so on and so forth. But there were some challenges here. So historically, categorical variants had the big problem of not being computable. They didn't really mean very much to computers. So an example here is MET delta X14, where in the literature, that string MET delta X14 refers to MET exon 14 skipping mutations. And this is difficult to compute on for a number of reasons. For one thing, delta is not a common or standard part of any common nomenclature in human genomics that I know of. So that doesn't really make much sense. And in this case, sometimes people use it to mean like change, but here it's a very specific change. It's an exon skipping change, which is also weird, right? Doubly weird. Going down from this transcript change to underlying genomic variants, such as an intronic genomic variant, which can give rise to exon skipping, is a non-trivial thing to compute. Alignment on your transcript can also change which exon we're actually talking about. So exon 14 on the main select transcript might translate to exon 13 on a different transcript, or 15 or 16. Finally, MET exon 14 skipping mutations are similar in clinical effect and importance to MET amplification variants. But there's nothing really about the string MET delta X14 that tells you that and makes that obvious. So until now, we had to rely on personal experience and intuition to make that leap of logic. And Cat-VRS hopefully will help us with this. The second problem that Cat-VRS is trying to address here is that extensional modeling doesn't scale. And what I mean by this is if we represent categorical variants as sets of variants, one way you can represent the set is by saying, hey, here's this label, and here's the members of this set, right? Member 1, member 2, member 3, member 4, member 5. So in this example here, we have a bunch of shapes. We have a set of just these things, which happen to each be orange squares, right? So this thing and this other thing, that's the set. That's extensional modeling. And this is how a lot of knowledge bases like Civic have in the past approached the problem of representing categorical variants. It would say, hey, we have this class of variants, and here's all its members. And this doesn't scale, unfortunately. It's inefficient to curate as information changes because you have to go back and update all those records. And a lot of categorical variants are so large that this just is not plausible. So if we talk about the categorical variant EGFR exon 19 sequence deletions, for example, there's about 10 to the 125 possible members of that. So if this circle represented an upper estimate for the number of atoms in the universe, and that was 1 centimeter in size, then the circle for this category would be about twice the size of the Milky Way galaxy. So it's just not something you can list out and compute. We need a better way to do this. So here's how we designed Cat-VRS to help with this problem. First thing we did was after sitting down and talking with the folks on the ground who work on these knowledge bases, we said, okay, what do people mean when they talk about categorical variants? When they refer to one, when they make up a new one, what are they actually trying to communicate? And the answer turned out to be a relatively small number of common properties, right? They might be talking about a particular region that a variant's in or a change in that location. They might be talking about a quantitative change related to copy number. They might be talking about a function change, or so on and so forth. So these individual properties that come up again and again and again that were clinically interesting or relate to biological underpinnings. These are the kinds of things people are trying to refer to. And so we said, well, what if we represent that? So one complication of this, which we'll come back to, is the fact that these can be extremely vague. So you could be, or precise. So a location could be as precise as this exact nucleotide in this exact part of this, exon of this gene. But region could also be as vague as just chromosome 11 variants, right? Which is incredibly broad. So that was an interesting challenge to model, but we're able to address it. So the answer to our earlier problem was to not be extensional, but to model categorical variance intentionally. So what that means is instead of listing out the members of each categorical variant, to instead define each categorical variant by its common properties, by the properties required of all its members. So an intentional set example is here on the right side, where instead of saying the set of these things, we're saying the set of things that have these properties that are orange and square. And as long as we can make those properties computable, understandable by computers, we're good, right? We can represent categorical variance that way. And so that's what we did. We developed a novel architecture for Cat-VRS, the data model, which is called a constraint-based model. And each of these constraints represents a property of the categorical variant that people are trying to model. So these constraints are explicit. They let you to say exactly what you mean. They're computable in that computers can understand them, and that they're human aligned. So by that, we mean they're fairly intuitive once you get the hang of it. We try to make them mean exactly what they seem like they should mean. So hopefully people, once they learn the system, it becomes second nature to understand how you would characterize something, and you'd be less likely to misuse the system by accident. So if someone's talking about a MET delta X14 variant, as we saw earlier, what they're really talking about is a variant that's in the MET gene and relates to exon 14. It causes a gain of function as a net effect, and it relates to a particular transcript sequence deletion where you've lost exon 14. And if those three boxes are checked off, you know you are looking at a member of this class, regardless of what else you know about it. So that's what we designed Cat-VRS to do. We were able to translate these different properties into different constraints that then exist in the model and allow computers to check off the boxes in the same way that you can do this sort of intuitively. So this particular variant in Cat-VRS might look something like this, where now we have that same name, but it's just a name. And what we mean by that is captured by these three modular little buckets of information. So the first top one is telling the computer, hey, we're talking about something that's in this place we're going to call MET exon 14. And if you want to know what that means, go look up this UniProt ID and know that that's what we're talking about. We're also talking about something in the bottom box that has a function change. And the kind of function change we're going to call gain of function. And if you want to know what gain of function means, computer, go look at sequence ontology code 1000125. And that's exactly what we mean, right? So these kinds of recurring modular boxes let us plug in information to describe these categorical variants in a way that's reasonably representative, intuitive for what humans think about when we're talking about categorical variants, but also is understandable for the computers to allow us to automate a lot of processes around these things. The middle box here, defining a allele constraint is saying, hey, there's a transcript variant that looks like this, and it has a unique identifier associated with it. So you could go out and match that too, and also understand what that means. Another advantage of this type of architecture, and this is what is sort of written at the very top, is that because these are little modular bits of code that are fairly open, this is somewhat of a bring your own ontology kind of system. So if you like using sequence ontology, you can refer to those concepts in here as we did below in the function constraint. If you had a different ontology you want to use, like the Odyssey standardized vocabularies, you could also bring those ontologies with you and use them in the system. Coming back to that challenge I alluded to earlier, one issue, right, was that categorical variants can be extremely specific or rather vague. Um, and the nice thing about the constraint system is that it handles both of these. So the system is built to allow people to input the information that they know without forcing them to make up information that they don't know, which protects data provenance and makes it helps us reflect the human intuition and the knowledge associated to us available. So to go back to this example, actually, if you imagine that someone was reading a journal article and it said, "Hey, in conclusion, met exon 14 variants are associated with X, Y, and Z." If that paper doesn't tell you what version of MET you're talking about, doesn't cite a HG&C ID or an ensemble ID or a transcript, you might not know what the coordinates are for exon 14, right? If you do, great, we can be specific. We can put in the coding here. We can put in the relation. If you don't know what that means, you just say, well, all I know is it's this thing called MET exon 14. You would put that top bit on, and you wouldn't be any more detailed than that. And so when someone accesses that record down the line, they know that they can't be any more specific because the underlying evidence item that you took this from wasn't any more specific than that. So um, that's a nice feature of this. The other payoffs of this are to allow you to search categorical variants in novel and interesting and very useful ways. So previously, a lot of matching and search of categorical variants was done by string matching, right? You would type in the name, you would look for that. And partially because there's a lot of different kinds of classes, they overlap, they might be written differently. There was lots of cases where some of it can be very hard to find the right string to find the information you need. And once you have a variant in Cat-VRS form, you can then search by these constraints and do matching by them. So here we have two categorical variants. They both have different names, but if we look at the constraints, we can understand very easily and naturally how these categorical variants are related to each other. So this guy on the left has a feature context constraint, same as the previous one. We know that it is in something called BRCA1 or BRCA1. We know that that is something that in their system we're saying is a gene. If we look at the second variant, that feature constraint is the exact same. So you know that they're talking about the exact same region of the genome. They're talking about the same feature. Cool. What about the next one? Well, we have a copy count constraint here that's talking about a copy change. And here it's just saying we're talking about exactly 4 copies here that were observed. Okay, what this pertains to. Well, the second variant is talking about a range of copies from 3 to 7. So by lining these up, we can very easily see that this category on the left of that's labeled BRCA1 copy number gain is really a subset, a subpart, a subgroup of this variant on the right. And so any knowledge associated with the one on the right should also apply to the one on the left, but maybe not necessarily the other way around. So in conclusion, Cat-VRS provides a fair infrastructure for categorical variant semantics and meaning. It provides semantics that computers can use, which will help us implement all sorts of automated workflows into our clinical practice. It supports both the precision and imprecision that is endemic in human expression. It addresses an open problem in variant representation in the categorical variation space, enables novel strategies for search and curation, and it brings new efficiencies to research and clinical genomics workflows. So Also, as Melissa Klein noted earlier, this is part of the ecosystem of GKS standards, and they are all intercompatible with each other. So, Verse, which was released in 2.0 this past summer, specifies individual molecular variants, which can be themselves members of categorical variants classes. And those categorical variant classes can, in turn, be taken as subjects of genomic knowledge statements in the Variant Annotation Specification. So these are all interrelated, they're all intercompatible. And once you learn one, a lot of the data model components are recycled in other standards. So the bar to learning a new one is much lower once you've already gotten one under your belt. Um, since Cat-VRS was released, we also are bringing it to a lot of knowledge bases near you and other resources. There's been a lot of interest in using Cat-VRS because of the benefits it brings to search and curation, and so look for it in a resource near you soon. Currently, it's live in ClinVar GKS, and it's slated for inclusion in future versions of DGI-DB, Civic, as well as the Vic MediKB. And there's also some other implementations, such as the Alimo Informatics implementation, which is using it for therapeutic indication matching and clinical trial inclusion criteria matching. And you'll be hearing about Epic Systems, our colleagues at Epic Systems who are using it in their data models as well in a couple of minutes. So with that, I'd just like to thank, oops, these boxes got shifted down, but to thank especially my co-lead, Brendan Reardon, and our wonderful admin, Beatrice, with whom which none of this would have gotten done. Also, apparently Alan Rubin, because the fate wanted that. But that's what I got from my presentation. If there's any questions in the next couple of minutes before I need to hand the floor over, I'd be happy to take them. If any of that didn't make sense or did, and you want to talk more about it, um, happy to hear. And if there are none, you can always email me after this or catch me on Slack in the GA4GH Slack. And I guess I'll hand it over to our friends over at Epic.
Cool. Thank you, Daniel. I will share my screen. Okay, can everyone see my screen?
Yes.
Cool. So I'm Mrinal. I'm joined by Catherine Taylor. We also work with Catherine Prochnow. All of us are software developers on the genomics team at Epic, which is a healthcare software company. So just a little bit about background about Epic to start us off. So Epic is about 45 years old, coming up on the big 50. We were founded in 1979 by Judith Faulkner, who is also a software developer. She actually wrote our first database code, which sort of lives on in spirit today. And she's still our CEO. And all of us are working in person together here in Verona, Wisconsin. So these top four pictures here are of our campus in Verona, and the like white sort of country looking building. That's where Catherine and I are right now. That's where we work. And Epic has customers all over the world in many different sizes, many different workflows, many different levels of complexity. And when our customers purchase Epic, they purchase a system. So they own the source code. They choose which modules and features they want to use, and they own all the data. Epic doesn't own that data. And most customers actually host the system themselves. So the servers, all the hardware is actually on their site. So originally we started with software to treat patients in the hospital and the clinic, but our footprint has extended beyond those settings to just about every area of healthcare. At the center of our software remains the concept of a single integrated patient record that can flow seamlessly to each of these areas and enable the best care for patients. Catherine and my job on the genomics team is to integrate genomics data whenever and wherever it's relevant to take care of patients, including many of the areas on the screen here. And our users include those taking care of patients who might need genetic testing, like geneticists, oncologists, neurologists, cardiologists, etc. It also includes patients themselves, most of whom access their health data, health record data through our MyChart patient portal. And we also support directly and indirectly research on healthcare data via reporting tools. And then finally, we also have an integrated lab information system called Beaker, which means our users also include pathologists, variant scientists, technicians, geneticists in the lab. And we actually have a lot of development going on in this area right now, which Catherine will touch on in a few slides. But before we go into the lab workflow, I wanted to zoom in on the clinical workflows first. So in those clinical workflows, discrete structured representations of variant data and associated knowledge are critical to making genomic results actionable in each of the areas on the previous slide. So this includes things like customizing education presented to patients and providers based on genetic testing results. It includes automatically adding patients to registries and health maintenance topics based on genetic risk factors like BRCA mutations. And it also includes tying genomic data into existing clinical decision support tools across many different clinical workflows, such as prescribing medication, treatment plan selection, research study recruitment, and others. And all that functionality is based on discrete structured data, and standards-based data exchange is the way we get those structured representations of variants and knowledge. To give you a very high level overview of the workflow, many genetic testing workflows start with a clinician ordering a genetic test directly in Epic, which automatically gets sent to the lab. The ordering clinician and the lab may or may not be both on Epic, and they may or may not be both part of the same organization. If the lab is a separate organization, Epic software can discreetly and automatically transmit the order to the lab and receive the incoming results structured using HL7v2. As genomics evolves, we often find ourselves needing to extend the HL7v2 specification to represent new fields, new types of variants, new types of knowledge. And as we make those extensions, we basically base them off of the GA4GH standards and just take those models and try to fit them into HL7v2, but keep them conceptually aligned. An upcoming example of this where we're planning to use the GA4GH standards is with support for receiving breakpoints over HL7v2. We're basing that off the GKS adjacency model and the VIC fusion standard. Additionally, once the patient's data is in the chart, the genomic data, along with a lot of other important chart data, can be transmitted to other software for decision support, reporting, etc., using the HL7 FHIR standard, which we're currently using, if you're in the FHIR lingo, R4 for. I think importantly, since we're keeping our internal data model conceptually aligned with GKS, having FHIR R6 also conceptually aligned with GKS will go a long way in terms of being able to transmit data seamlessly between these two standards without losing any meaning. So shout out to Bob Freemuth and his team for that work. And then finally, we're also interested in using GKS to integrate with knowledge bases in both clinician workflows and the lab. And that's what a lot of the rest of our presentation with Cashman will talk about, will be about.
Yeah, so our current project that Mrinal's kind of hinted at, where we're doing a lot of work kind of in lab workflows, is we are developing a tertiary analysis workflow within Epic. And this project aims to remedy some of these, fragmented multi-software workflows that we're seeing our customers, currently deal with, and we have seen them deal with for a long time. So kind of the short version of what this tertiary analysis pipeline will do is it'll match VCF data to up-to-date genomic knowledge bases to enable annotation, filtering, and interpretation of genomic data before it seamlessly enters the patient's chart, all within Epic. So central to this matching algorithm that we're using to match these variants to annotations is a unified data model to represent all the varied types of data in these knowledge bases. So that is exactly where GKS is going to come in. So this is a lot of words on the screen. Hopefully I'll be able to break it down. But this is just a rough diagram of how we're currently using GKS standards in our tertiary analysis pipeline. We do have, I will go over a couple of future plans as well. We have a lot of future plans. This is not the end state by any means. But this kind of goes from, start to finish. So first you'll start with variants on a VCF, which are run through a parsing algorithm where we'll extract some of the VCF metadata, and we'll also kind of transform the VCF data to represent the variants as a verse allele. We also lift over these VCF variants where necessary from GRCH 37 to 38, for example. So both of these, both the raw and the lifted over alleles are going to be represented as a canonical allele. And then we also are currently using several of the Cat-VRS constraints that Daniel just talked about. They're specified in the blue column to kind of add that additional context there. Then once we have all of our VCF variants represented as alleles, that's when we'll run our matching algorithm to annotate each of the variants. And like I said, this matching algorithm matches the alleles to a wide variety of annotations from the genomic knowledge bases, which are up on the screen in purple. In order to get these annotations into EPIC, we import the knowledge base data in the native format, which may or may not be in according to GKS standards. It might be in the future, it might be now, or it might never be. So if needed, we will perform a transform. So we'll convert the data into GKS standards whenever possible. And then the orange column kind of shows the results of that transform. It shows the current VA-Spec data models that we're using. There are also a couple things in orange that are things that we have kind of identified that we really want to get into the VA-Spec as well, that Mrinal and I will go into more detail on in later slides. And then the final call out before I move on to the next slide, you might notice the internal knowledge base blurb at the bottom of the screen. So that's something that is EPIC developed, but it mimics a lot of the internal knowledge bases that our customers will have for their previously interpreted variants in their lab, and that we're also using GKS standards as well. So that makes matching to VCF variants much easier, as well as potentially submitting to ClinVar down the line or anything where we would be exporting this data. Cool. So now Mrinal and I are going to kind of go back and forth on some of the implementations with some of the knowledge bases that we've either are still working on or have recently completed. So I'll first start by talking about Variant Effect Predictor, or VEP, which is made by Ensemble. And this was one of the areas where we were getting these annotations from VEP that weren't necessarily well represented by the current GKS standards. So we ended up kind of talking to some of the GKS leads. We've been working with Alex, Larry, and Matt quite a bit, as well as some folks from Ensemble. And we're currently working on creating molecular consequence and functional predictor score standards to add to the VA-Spec. So currently what we're doing is we're transforming VEP's native output into our own data model that we've, kind of mimicked the proposed standard to the best of our ability. And then now, since we have Ensemble on board, our long-term goal is to ingest VEP's output that will be produced directly in the GKS format. So we don't have to do any sort of transform. We'll just be able to ingest it directly, which will be super great in terms of maintenance and kind of upkeep of our pipeline. We have faced a couple of challenges with this implementation that I will share. Our first challenge is just sort of those rarer variant types. So intronic variants are a really good example of this. They're not necessarily well represented by VRS or Cat-VRS yet. Obviously, things are moving in both of those work groups to kind of get those different variant types represented, which is awesome. But overall, we have identified a few places that kind of pose the need for another standard that can be used broadly. We've also observed different molecular consequence terms being used across some standards. So VEP uses sequence ontology, which is probably much more widely used. But like Mrinal said, we are accustomed to the HL7 V2 model, which has a couple of additional terms that have been tacked on to sequence ontology. So that's always fun. And then finally, with any standard, we've obviously been looking to generalize this to the best of our ability. However, there are just so many different, predictor score that VEP can output. And we're really trying to, make sure that we've covered all of these different types of scores to make sure that any type of functional prediction can be represented. However, despite all these challenges, we've made a lot of progress over the past year, and we are super excited to see these standards become part of the VA-Spec in the future. Back to Myrtle.
Yes, I'll take over because I worked on ClinVar integration with Larry. So for those who don't know, ClinVar is a really important resource in genomics. It's a resource that both our clinicians and lab users are really interested in. And I would say, just like broad statement, that the ClinVar GKS dataset that Larry and his team have created is really, in my mind, like a model of how standards-based knowledge exchange should work in the future. So to give you like the historical perspective from our like integration with ClinVar, originally we used the ClinVar XML dataset, and that had a lot of lift to ingest the data, make sure we were understanding the fields properly, and to make sure we were properly matching the ClinVar data to patient variants in like all the different forms that they could be in. And it was a lot of work. And then we learned about this work that Larry and Alex and the GKS team are doing. And I think probably about a year and a half ago, Larry gave us his sort of pre-release data set during the Ascona Connect. And that was already a huge improvement over the XML data set. But there were a lot of minor differences between like his data model and the one I was using internally. So there was still some lift for us to transform from his data into our data and ingest it. But over the last year or so, the standards have really matured. So Cat-VRS and VA-Spec had 1.0 releases coming out and entering trial leaves. And at the Uppsala plenary a couple of months ago, Larry gave us his latest data set, and it was really amazing to see how seamlessly it integrated. So we base all of our internal data models on GKS, and then we could just use the standard JSON deserialization in C# and deserialize it into our data model, ingest it, and it worked out of the box. Basically, like no overhead to transform, and that was just super awesome. So you can imagine scaling this like across the industry, like it could really reduce the overhead required to integrate with all these different knowledge sources and exchange data. So if you're someone who is developing software for knowledge bases or developing software for tertiary analysis, I would definitely recommend checking this out. Moreover, Catherine mentioned the internal knowledge base that a lab could maintain is also aligned with GKS. And so that gives us a lot of benefits downstream in terms of being able to consistently query the data and display it in various places. And we're excited to continue working on this ClinVar integration and expanding it with RCV and VCV data sets, and also using the GKS to ClinVar submission tool to submit data back from these labs' internal knowledge base to ClinVar. Shout out to Corey Kuzma for developing that. And then we also have an integration with Nomad. This integration isn't as nice here, but it still works pretty well. So for Epic, I mentioned earlier, we have customers in a whole range of scenarios, different sizes, different levels of complexity. Many of them are still on build 37 and they're still using Nomad V2. Some of them are on build 38 and they want to use the latest data. And we need to support all these customers in different states. So we need to support multiple versions of Nomad. So what we decided to do was ingest the Nomad VCF data ourselves and transforming into the GKS data models. We still heavily reference the existing Nomad GKS transform that they did for V4 while developing this. So shout out to Kyle Farrager, whose work was super helpful to us. And we basically, yeah, just took a lot of what he did and applied it to V2 and V3. So that includes things like nesting subcohort allele frequency study results and including ancillary results. And we're also looking to expand this Nomad integration in the future, potentially include constraint data as well. And then dbSNP, similar story to Nomad. We parse the raw dbSNP JSON and transform it into GKS data structures. dbSNP doesn't really offer structured knowledge per se, so we only use verse and cat-verse for dbSNP. And there are a couple of things that didn't fit perfectly into the GKS standards. So we can go into more details about that if you are interested and you have time. But there's questions like, where should these sort of like variant level literature links live that aren't really associated with a VA-Spec statement? And how could we store like multiple defining locations for a categorical variant across different builds? And then I'll hand it off to Catherine to talk about our future plans.
Yeah, so like I said, we have a lot of future plans. Our tertiary analysis project is still heavily under development, so we have lots of exciting things we're still planning to do. First and foremost, kind of the obvious thing is we definitely plan to integrate with more knowledge bases, one of those being Civic. Civic, I am, very excited to integrate with because they've already done a lot of that work to adopt a lot of the GKS standards. So like Mrinal said, with, ClinVar, we originally didn't have any, we were using the ClinVar XML and it was a huge pain to transform the data. But then, with Larry's latest updates and having everything already conforming to GKS standards, everything becomes a lot easier. So that's, one of the knowledge bases that I think will go a lot more smoothly for us. We're also just always on the lookout for any sort of new standard. I think some of the things we're particularly interested in are kind of like VCF level information, test metadata, and stuff like that. These are things that I think Mrinal and other Catherine have, talked about on previous calls and stuff. But we're since we have such a wide variety of customers, if there's, basically any way to represent genomic information, we probably have a need for it and need a standard for it. And one of the other things that we've been able to do is we've been considering some proprietary knowledge bases to ingest their data. We have been kind of encouraging these vendors as well to adopt GKS standards, kind of spreading some of that awareness. We honestly have received a little bit of pushback, mostly just, time constraints. But if we do hear any specific feedback about the standards from these vendors, that's, a great place for us to bring that up in future calls and see if we can, make those changes if there are any that come up. And then finally, jumping a little bit outside of GKS, we did recently complete some development to be able to document phenotypes as HPO codes directly on a patient's chart within Epic. And that opens up a lot of doors for us to be able to kind of export that data and exchange it with other softwares using some of the ClinPheno standards and FHIR. This is,
Sorry.
and then one slight challenge that we have noticed is there is some sort of, differences in phenotype representation between ClinPheno and GKS. Mrinal, I think, brought up the coding versus ontology being the first thing that came to mind. But overall, we're very excited to kind of work in that direction as well. And then finally, I think we have been involved with Verse and Cat-VRS over the past couple of years, so it's been really exciting to see all of like the new variant types that have been able to be supported. I think like Cat-VRS version 1.0 being released was like a huge step. But again, like we do, if there's any sort of variant, there's a possibility that we will get this variant and need to be able to represent it for our wide variety of customers. So here are some of the things that we are kind of looking forward to new standards or changes to the existing standards to better be able to support. These are kind of things that have come up with some of our knowledge-based integrations or that we just kind of have on our general radar. So we'd be excited to see things about these variant types as well. And I think that is it.
Yeah.